stop good.
Okay. So, good morning, everybody. And now we would like to deal with the mathematical programming. And it is a non-linear. In this one, we talk about the non-linear programming. Most importantly, here, the aim of the session is to familiarize the basic concepts of the geometric programming and with and without constraints. And the instructional objectives are to demonstrate the geometric programming with and without constraints. The learning outcomes are to define and understand, apply and the concepts of the geometric programming and their applications. Geometric programming is a special form of the nonlinear programming. We motivate its study through an example here. Now here it has got a practical application, and we see here a gravel box design. 400 meter cube of gravel box is to be ferried across a river on the barge. The box, it has got an open top, is to be designed for this purpose. Now we have got a gravel and we have got a box and we have got the barge. Now here what we need to do is the cost is to be calculated. The transport cost is 10 cents per round the trip, and the materials are sides bottom of the box are 10 meters square and ends of the box are 20 meters square. What should be the optimal dimension of the box and the barge and the gravel? That's what we need to evaluate it. Now we form a mathematical formulation. X1 is the length, X2 is the width and X3 is the height. And the material cost is 2 into 20 X2 X3 and 2 into 10 X1 X3 the sides and 10 X1 X2. Now this is the total volume and it is the material cost. The transport cost is X1 X2 X3. The number of trips that are required is the smallest integer, which should be greater than 400 by X1 X2 X3. And approximate cost is less than 5 cents, therefore it is 0.1 into all the above factors here. So here the total cost function that is given by fx is 40 by x1 x2 x3 plus 40 x2 x3 plus 20 x1 x3 plus 10 x1 x2. And here we use the Cauchy-Coon-Tucker condition and we find the differentiation with respect to x1, x2 and x3, because x1, x2, x3 are the parameters that are involved in the problem. The first partial derivative we will take it and equate it to 0 here. Now here, now all these parameters when they have calculated here, in general this appears to be of this much, where CIB is strictly the positive here. The geometric programming here, it is divided into sinomials and signomials here. And here back to the gravel problem, the function fx is the transportation cost, the ends, sides and bottom. All these things are to be evaluated here. That is a delta 1 star we define, delta 2 star, delta 3 star and delta 4 star. That's what we find out. Then the normality condition is that the sum of all these things should be equal to 1, and the orthogonality condition is that it should be always equal to 0. So when we evaluate it, then the equations what we get is delta 1 star plus delta 2 star plus delta 3 star, delta 4 star, that is equal to 1, that is the normality condition. And for x1, x2, x3 we have got separately the conditions here. And Gauss-Jordan application, when we apply here, delta 1 star is 2 by 5, that is 40%, delta 2 star is 1 by 5, that is 20%, delta 3 star, that is 1 by 5, that is 20%, and delta 4 star, that is also equal to 1 by 5, that is 20%. That is what we will be having here. Okay, so now here it follows that x1 to the power minus all this x2, similarly x3, that should be always equal to 1. The sum of the product of all these things should be equal to 1. That means ultimately we will be having f star of delta 1 star by 40 to the power delta 1 star. Similarly for delta 2, similarly for delta 3 and delta 4, that should be always equal to 1. That means f star is given by this equation. That means 40 by 2 by 5 to the power 2 by 5, 40 by 1 by 5 to the power 1 by 5, 20 by 1 by 5 to the power 1 by 5, and all these things, that comes to 100. Thus, the minimum cost of the box should be $100. Again, back to the Gravel's problem here. How do we find the optimal values for the primal variables xi star? Now this is what we need to evaluate it. So here 40 times by x1, x2, x3, that should be 2 by 5 of 100, that is 40, and 40 of x2, x3, that is 1 by 5 of 100, that is 0.5, 20, that means 0.5, and 20 x1 x3, that is 1 by 5 100, that is 20, that is equal to 1, and 10 x1 x2, that is 1 by 5 of 100, that is 20, that amounts to 2 here. So here the non-linear system is easily linearized by taking into the logarithms here. We take the natural logarithms, and this is the set of equations what we will be having. And ln of x1 star we call it as z1, ln of x2 star we call it as z2, and similarly for z3, and finally what we get here is minus z1 minus z2 minus z3, that is equal to 0, and so on, and ultimately this leads to the solution of the equations. Z1 is ln of 2, z2 is 0, and z3, that is 0.5. Therefore, x1 star is 2 meters, x2 star is 1 meter, and x3 star, that is 0.5 meters. The number of trips that are required are 400, and the minimum total cost is 100. Finally, this would be the solution of this. Okay, so this is how a problem is evaluated here. And here, and a closed storage tank. Now to design this one also, the cost of the material is $1 per meter square. The required volume is 1000 pi times a meter cube. Now this is what we'll be having, and this is to be optimized, so the cost has to be minimized. Therefore, top plus bottom plus sides, and all these things, it has to be minimized. Okay, so here the normality conditions are delta 1 plus delta 2 equal to 1, delta 3 is lambda 1, delta 2 minus delta 3, that is equal to 0. That's what we'll be having. Ultimately, the 4 equations and 4 unknowns, when they are solved, delta 1 star is 1 by 3, delta 2 star is 2 by 3, delta 3 star is 2 by 3, and the optimal cost is 1187.45. Therefore, the optimal primal value, that is equal to $1187.45, and computing the dimensions, x2 star, that is equal to 7.937, x1 is 15.874. The optimum height, that should be 15.87 meters, and radius should be 7.937. Now this is what we will be having here. So this is how a problem is evaluated by applying the mathematical programming concepts. I hope it is familiar for everybody, and please try to understand the problem and try to find out the applications as and when you see here.